All right, so this mini lecture is going to look at how do we mathematically determine an object's velocity from a position versus velocity graph. What is that relationship mathematically? And it's going to overlap a little bit with our initial description of constant motion, and then we're going to use that to figure out how we do it with a non-constant motion, with an accelerating object. So let's look at getting the velocity from a constant rate to constant motion. And if the velocity, we have to keep in mind that the velocity is equal to the slope, the rise over the run of an object's motion, the slope of that graph. So if I want to look at the velocity between two time points, we'll say time 1 and time 2. I want to take the slope of the graph between time points 1 and time points 2. So my rise would be delta x and my run would be delta t. My rise, my change in position, over my run, the time I'm looking at, the change in time. So my velocity in this case of constant motion is equal to delta x over delta t, my change in position over my change in time, the slope. And that's what we talked about before, and it's pretty straightforward. So what about if I have an accelerating object? Well, let's say I want to find the instantaneous velocity at this time point t. So we've said before that that instantaneous velocity is the slope of the tangent. Well, how do I get that slope? Here it was pretty easy, rise over run. But how do I get it on a curve situation? Well, let's think about this as what would be my best approximation? If I had to guess at the velocity at that point in time, how might I do that? Well, one method is that I might sandwich it. I might say, well, if I look at the average velocity between these 2 points in time, equal distances of time, the average velocity is just the straight line distance between those 2 points in time, the straight line slope, the slope of the straight line between those 2 points in time. It's not a great approximation of the true tangent. Remember that true tangent is going to have a slope that looks more like that, but it's not too bad. But I would like something better. How can I get better? Well, maybe I could sandwich it even smaller. Instead of these 2 wide points, what if I took these 2 points that were closer together? Oh, well, now that slope is starting to look like the slope at the tangent point. But I bet I could even do better. What if I took even smaller sandwiching of that point in time? When I'm still crossing that curve at 2 spots, but they're really close together. I'm getting better and better and better. Now, if I look at the slope for each one of these lines, I have, for the blue line, I'm going to have a change in position over a change in time that's represented by this blue difference in time. And for the orange velocity, I'm going to have the change in position over the change in time that's represented by this much difference in time. So here's my delta t for the orange. Here's my delta t for the blue. So these are average velocities. They're my approximation of the velocity at that very specific point in time. And we see that for my pink gas, it's between those 2 points in time. So what am I doing as I move from my blue estimate to my orange estimate to my pink estimate? I'm getting tinier and tinier and tinier points in time. I'm looking at the change. I will put it in green. I'm looking at the change in position over my change in time as my change in time goes to 0. So hopefully that rings a bell. If I look at a change in position or a change in one variable as a function of a change in another variable, as that time variable, my second variable, gets closer and closer to 0, this turns into a derivative. And this is what becomes important. As I go smaller and smaller and smaller, changes in my run, changes in my time in this case, my velocity is actually the derivative of the position as a function of time. And we know position is a function of time, the object's position during various points in time. So this becomes our most generic relationship between velocity and position. It's not average velocity, it is the velocity. The velocity at any point in time is the derivative of the position versus the time graph. Does that work over here? Does it give us what we want over here? Well, yeah, it does, because as these 2 points in time get closer and closer together, I'm still along that same line, and I'm getting the same velocity value as I do that's constant along that line. So we're going to utilize this idea to look at various position relationships, whether it's a single curve and a single accelerating motion, or a linear graph and a linear a constant motion, or if the motion follows some funky function. Regardless, the position, the derivative of the position as a function of time, gives us our value of velocity or our relationship for velocity. And we're going to do some of those examples in practice and in another mini lecture. All right, good job.